Welcome to this explainer. Look, if you're working at the intersection of machine learning and physical systems, you're probably intimately familiar with a very specific, very frustrating theoretical tension. On one side, we have classical physics-based state space models, like your traditional Kalman filter. They're elegant, they're physically interpretable, but let's be honest, they completely crack under the pressure of complex, nonlinear, and uncharacterized noise in the real world. On the other side, we have deep learning black boxes. Sure, they can map almost any nonlinear relationship if you just drown them in enough data, but they offer zero physical interpretability and they notoriously fail to generalize spatially. So today, we're diving into a fascinating framework called QNet that frames this exact tension around a classically brutal civil engineering problem, urban traffic queue estimation. QNet is an AI-augmented Kalman filtering framework that finally synthesizes those rigid physical models with adaptable neural networks, and it does it brilliantly.
So here's our roadmap for today. We'll breeze through the foundational headaches of the urban queuing problem, dig into state space modeling under partial observability, and unpack the nonlinear measurement model. Then we'll hit the really good stuff, learning the Kalman gain with AI, solving spatial transferability, and finally looking at the real-world validation.
Let's kick things off with the core issue driving all of this: partial observability in urban queuing.
To really grasp why a hybrid approach is necessary, we have to face the primary obstacle in monitoring signalized intersections. Our data is practically never perfect. Think about the physical reality of an urban intersection. You've got these unobserved flows, vehicles sneaking in from side streets or unsignalized driveways, and they completely wreck standard input-output conservation models. Traditional models rely on strict traffic conservation, assuming every vehicle entering the system is counted and every vehicle leaving is counted. But out in the wild, vehicles are constantly leaving the main queuing path before ever hitting a downstream loop detector. Over time, these unmonitored paths accumulate, causing massive compounding drift in your baseline queue estimates.
Now, a traditional Kalman filter demands no noise covariance to handle this, but honestly, that's a laughable assumption for dynamic urban traffic. The noise is highly nonlinear. Meanwhile, pure neural networks act kind of like data-hungry toddlers. They might furiously memorize the specific noise patterns of one single intersection, but the second you ask them to generalize to another one down the street, their spatial transferability completely falls apart. This massive gap is exactly where QNet steps in to give us the best of both worlds.
Moving on to the state space formulation, let's see how we can actually preserve the underlying physics.
The genius here is how QNet maintains strict physical interpretability within its state evolution model. We aren't just chucking raw data into a neural network and crossing our fingers. In any state space model, the state evolution dictates how the system moves forward temporally. For QNet, our control input UT explicitly represents the physical queue change. By taking the cumulative inflow and outflow counts from the detectors, we actually mathematically adjust for that unobserved flow we talked about, represented as lambda c. By estimating lambda c using pre- and post-peak boundary conditions, we derive a reconstructed queue length proxy, LPUT. This step is absolutely crucial because it anchors the entire model deeply in macroscopic traffic flow theory. But as you might expect, raw reconstructed queue proxies are incredibly noisy. So what the researchers do is apply a Fourier bandpass filter to isolate the medium frequency variations. This elegantly strips away the low-frequency drift caused by those changing unobserved flows, while simultaneously wiping out the high-frequency jitter from raw detector errors. What you're left with is a clean, physically representative control input ready to drive the prediction step of our filter.
Next up, let's explore the nonlinear measurement model and how it bridges some wildly different data granularities.
We need to build a connection between our hidden queue state and our secondary data source, aggregated floating car data, or AFCD. This data gives us aggregated speed readings across whole road segments. But think about it. How do you accurately map a spatial queue length to a single aggregated speed value? QNet solves this using a two-state traffic representation. Basically, vehicles are either cruising at a free-flow speed or they're stuck at a congested jam speed. The measurement function figures out exactly where the physical boundary of the queue sits within a segment. If a segment is partially queued, the expected speed becomes a nonlinear mapping based on the travel time required to cross the unqueued portion versus the queued portion. This flawlessly preserves the macroscopic reality of traffic flow and builds a physics-informed bridge between our high-frequency point data and our low-frequency spatial data.
Before we get into the AI magic, I have to highlight this one detail because it's fascinating from a theoretical standpoint. Throughout the predict and update steps, QNet utilizes a projection function.
Now, classical Kalman filter theory absolutely despises nonlinear projections like this because it completely shatters Gaussian optimality. But QNet forces it anyway. Why? Because the physics demand it. You simply cannot have a negative traffic queue, and a queue cannot magically exceed the physical capacity of the road section. By enforcing this projection, QNet guarantees the algorithm stays tethered to the physical constraints of reality. Optimality be damned?
All right, Section 4. This is the climax of the framework. Learning the common gain via an AI-augmented update.
This is where we weaponize machine learning to handle all that complex, nonlinear noise. In your textbook Kalman filter, the Kalman gain is computed analytically based on known, fixed noise covariances. But in QNet, those covariances are fundamentally unknown and constantly changing over time. So the loop detector data drives the a priori prediction state based on physics. Then, the low-frequency AFCD speeds swoop in to correct the drift. But the actual bridge between them, the Kalman gain that decides how much to trust the physical prediction versus the noisy sensor measurement, that is computed dynamically by an adapted Kalman net.
This adapted Kalman net utilizes gated recurrent units, or GRUs, but it doesn't just blindly ingest raw data. It's fed 4 highly specific temporal difference inputs. It tracks the forward evolution difference, the forward update difference, the measurement difference, and the innovation difference, which is the crucial error between what was predicted and what was actually observed. By feeding these precise statistical relationships into the GRUs, the network is explicitly learning the temporal dynamics of the nonlinear noise, rather than just naively curve-fitting a dataset. It learns exactly when the physical prediction is reliable and when it needs to lean on the sensor measurement.
So, what about spatial generalization? Let's talk about local grouping and how it solves the N problem.
A glaring flaw of standard neural networks is their spatial rigidity. If you train a model on a road section with 5 segments and then try to deploy it on a section with 8 segments, the matrix math literally breaks. To achieve zero-shot spatial transferability, QNet groups the measurement and innovation differences into localized, overlapping vectors. Instead of processing an entire road section in one go, the Kalman net computes a local gain based only on a specific segment and its immediate neighbors. The final state update is then just the sum across these local updates. Because the parameter dimension fed into the network is now fixed strictly to this local group size, it becomes entirely independent of the total road section length, n. Meaning, you can train this model on one intersection and deploy it on a completely different one without a single drop of fine-tuning. That is a massive breakthrough.
Let's bring this all back down to Earth and look at the real-world validation.
The researchers put this architecture to the test using a highly complex, real-world dataset from Rotterdam in the Netherlands. They pitted QNet against both traditional baselines and purely data-driven models. And, quantitatively, QNet beats them across the board. If we look at the all-day root mean square error, QNet clocks in at 86.77. It edges out sophisticated, highly tuned tree-based models like XGBoost, and it completely obliterates existing multi-source baselines like TreeRProp, which sits way up at 114.25. But honestly, the raw numbers only tell part of the story. The architecture itself tells us why it wins so decisively. Purely data-driven models are inherently reactive. They have to wait to actually observe a pattern in the data before adjusting, which introduces this massive temporal lag during rapid queue buildup or dissipation. But by relying on the rigid physical queue evolution structure for the predict step, QNet completely eliminates that lag. The loop detector physics give us immediate, highly responsive predictions, while the AI-augmented update step dynamically smooths out the severe, nonlinear noise artifacts that plague aggregated floating car data.
To wrap this up, I really want to leave you with a broader thought to chew on. We've just seen how beautifully QNet synthesizes rigid physics with adaptable AI to solve partial observability in traffic networks. But let's zoom out. Partial observability and complex nonlinear noise are absolutely not unique to traffic. Think about water distribution networks, structural health monitoring, or power grid state estimation. How else could you deploy an interpretable hybrid Kalman net architecture to tame the noisy, partially observed physical systems in your own specific research domain? It's a remarkably powerful paradigm shift, and honestly, it's one that is absolutely worth exploring.